Let me start first. Do you have any questions on the problems assigned for chapter 2 before we start to do practice together? Okay, so I will do a problem involving heat transfer processes. So we give the following. We have a box, okay, characterized by heat exchanged at the top surface with convection and radiation effects. So let me draw it. So you have the following box. Now, they are telling us that this box is undergoing internal heat generation. Whenever we talk about an internal heat generation, it can be of different sources. So you can have, let's say, some chemical reactions taking place inside your material that will deliver some heat. Okay, you can have, for example, in case this is a chamber and you have combustion within the chamber, so you can have generation. So you have several possible heat sources. So whenever we talk about heat generation, in general, it is defined per meter cube, okay, because it is within a certain volume. So we give that the value of Q dot, so the heat of generation Q dot is given by 20 watt per meter cube. Now, our box is exchanging with at the level of the top surface only, is interacting with its environment, which is the outer environment. So we will tell you that no transfer is possible across the other surfaces. So if you want, these surfaces are well insulated. Okay. So this will not allow any transfer through these surfaces. We'll just have a transfer through the top surface. So this top surface is exchanging heat with the environment in several forms. Okay. First, they are telling us that it receives the top surface. So let us write here the given. So we have first heat generation. We call it sometimes volumetric heat generation. So it's per unit volume. So we have a heat generation within the volume. Equals to Q dot. Equals to Q dot given. So this is the first information. Second information, heat transfer with the external environment is only taking place at the top surface. Heat transfer with outer environment. Only through top surface. Okay. Sometimes in problems, they don't give you all numerical values. So you can, if they don't give you a certain numerical value, you can express your fluxes function of parameters. So let's say, for example, if they didn't give us what is this area A, we can keep it A into our equation. And you can see that a lot of times variables will be simplified. So A will figure out in all terms, so it will cancel out. Okay. So only through top surface. Now, what are the type of heat exchange of the top surface? Okay, first they are telling us that we have a convective coefficient between the top surface and the environment. So automatically then we have a convective flux. So you have an air stream going over your box. Okay, this air stream is characterized by a temperature T air equals to 25 degrees. Okay, and also they gave us that the convective coefficient H with the air coming across over the surface is equal to 5 watt per meter square per unit Kelvin. So it's 5 watt per meter square Kelvin. They also are telling us that the top surface is exposed is exposed to solar flux. Okay, so we have a solar flux that is equal to 400 watt per meter square. Okay, and in addition, we have they gave us the coefficient of absorption, okay, and the emissivity coefficient. So let me write here. In addition to all of this information, we have alpha equal to, so absorption coefficient equal to 0.95. And the emissivity coefficient epsilon is equal to 0.9. Okay, so we give all of this information to us, and they are asking to write the balance equation of temperature for the rectangular box, considering steady application. Okay, so this is the question here. In such a problem, how should I think? How should I divide my steps? So first, I should draw a scheme showing the different processes taking place. I will try to simplify a little bit. So I will, if you want, let us open another window to start from beginning. So let me save this. So this is the given. Okay, and now let us try to solve together. Okay. So the first step will be to draw like a diagram showing all heat transfer processes that are taking place. Okay, so first we have a rectangular box, as we said. Now we'll illustrate all, if you want, fluxes of heat and all generating sources of heat. So we have one source of generation that is volumetric. So it will, if you want, generate heat in all directions within your rectangle. So let us represent it by the following. So here we have like generation of heat in all directions. Okay. So this is Q dot, this is the volumetric transfer. And we can compute it. So let us put a certain representation for each energy source or flux and then find its expression. Okay. So this is, we said it's Q dot. Now, to start with, we can calculate the corresponding value of the generated flux. Okay, so I will call it Q dot generated. Okay, if you want to find the Q dot generated in what should we do here?
The volume is included.
Yeah, so we should multiply the area, okay, of this surface by the thickness, okay, by the thickness of our rectangular box. So if we call this T, okay, then we can say that the value of Q dot generation is equal to the value of Q dot, so which is 20, okay? So Q dot is given to us in watt per meter cube. So the unit here is watt per meter cube. To get Q dot generation in watt, we should multiply by a volume, and the volume is in meter cube. So we can replace V by the cross-sectional area times the thickness, okay? Now, if the thickness is not given, we can keep it function of the thickness, or also they can tell us, find, if you want, the energy equation per unit depth, okay? So if they ask per unit depth, then we can take T equal to 1, okay? So here, let us say T is given to be 1 meter. Okay, then we can write here that it's 20 times A times 1 equals to 20A. We are done with the first source of heat. Now, all other exchange between heat exchange flux between the box and the environment are taking place only through the top surface. So this is from given. And therefore, all other fluxes should be represented between the environment and the surface. Since they gave us the convective coefficient H, okay, and they gave us the environment temperature T infinity, so the second process of heat transfer is convection. So you have a flux going over your surface. This flux is characterized by H and T infinity, okay? And you can assume here a direction for your flux. So it can be from your box towards your environment or in the inverse way, okay? But you expect that since you have a heat source here, you might have high temperature of your box. So the flux, you can assume that the flux is from the box towards the environment, okay? And then if T surface is larger than T infinity, this will be right. If T infinity is larger than T surface, the flux will be in the opposite direction. So it doesn't matter if you do a wrong assumption, because when you do calculations, you will solve for your surface temperature. And then from the value of Ts compared to T infinity, you will know if really the flux is from the surface towards the environment or the inverse, okay? Now, if you represented your flux towards the environment, then, and you put this as Q dot convection, okay? Then you should say that the convective flux Q dot convection in total over the whole area is equal to, if you want, since we are just representing by one flux, we can put it as big Q. So it's the total exchange, okay, by considering the flux per unit area times the area. And here also I will put big Q dot generated, okay. Now, to get my convective flux, I have Q dot convection equal to, since I illustrated my arrow from the surface towards the environment, then I am assuming that Ts is larger than T infinity. So the convective flux is H times area times top surface temperature Ts minus T infinity. Okay, so this is my convective flux. Now, they also talked about a solar flux that is received by my rectangular box. Okay, so since since this flux is received, so I will draw it towards my rectangular box, and I will put that it's equal to Q dot solar. Please keep in mind that they gave us also the absorptivity coefficient and the emissivity coefficient. So we'll see how to include them. So we know the values of alpha and epsilon, okay? Now, if you want to calculate the solar flux, they told you that the solar flux received is equal to 400 watt per meter square. This is the flux per unit area. How to calculate the total solar flux absorbed by your box? What should you do? What is the formula which will give you Q dot
Using
solar?
radiation formula?
No.
Using the radiation formula, I mean?
What? No, you know why? Look, here radiation formula is based on alpha and epsilon equal, okay? And this is why when you use a formula, you should understand well its concept. وقت كنا نستعمل radiation formula كان عندنا two surfaces, okay, of different temperatures, and you have radiation flux from one surface to the other, okay? Here, did they define another surface for you?
No.
No. In reality, the radiative flux, you have a certain radiative flux. It's true, but because if you want, it's not just an exchange between two surfaces. The radiative flux here will be, if you want, at the condition of the surface itself. Any surface can emit, because it has a certain temperature, will radiate a certain flux. But to consider that it's receiving a radiation flux, you should have another surface opposing it. Do you have here another surface at a certain temperature emitting to your box? In reality, you have the sun, okay? And
exactly,
Q dot solar, yeah, exactly. In reality, you have the sun.
Said that they can receive it from the sun, radiation. It can
exactly,
absorb.
it's true. It's true. You can calculate it as radiative flux from the sun, but then you should define a certain temperature at the level, if you want, of your that will you have this flux that will go through the atmosphere, and then from the atmosphere you consider that you have T of the atmosphere, and you have these surfaces exchanging together, okay? Here, instead of going through all of this process and considering that the solar flux is received in a form of radiative flux by radiation between the top surface and the atmosphere and the atmospherical surface, They didn't go through these numbers. They didn't give you what is the atmospheric. They didn't go through these details. They just gave you what is the solar flux reaching your surface. Okay, so it's another way, if you want, to give you the flux. Instead of dealing with the atmospherical temperature and having to consider what is the emissivity of the atmospherical surface, etc., and how the radiative flux will reach Earth, they gave you in a simpler way all of this. They told you that the solar flux is reaching your top surface at 400 watt per meter square. So no need then, it's right that the type is radiative, but because they gave you the value and they didn't give you properties of the surface that will radiate this flux, you just directly say that Q dot solar that will be absorbed, okay, is equal to the absorptivity coefficient alpha times the flux that is reaching your surface. Okay, the flux reaching your surface is what? Is Q dot solar, which is the flux per unit area, times the area, the top surface area. Okay, so what I want you to do, I want you to understand well how they can give you data. Data can be given in different forms. They can just give you a flux without telling you what is its source or how it's reaching the surface. Here they told you it's a solar flux, and you know that solar flux will reach Earth by one of the type is radiative effects. Okay, so you can, but here no need to know that it's a radiative flux because they already told you it's reaching the surface at this value of flux per unit area. So just you have to multiply this flux by your area and to multiply by the absorptivity coefficient, because not the you know that the absorption coefficient will give you which portion will be absorbed by your by your rectangular box. Okay, is this idea clear?
Yes.
Okay, now because you have the top surface and this surface is characterized by a certain temperature Ts and the environment is characterized by a different temperature, you will have a radiative flux. Okay, so you have also Q dot that is emitted by your surface, and this is a radiative flux from your rectangular box towards the external environment. This flux, how you can determine it?
Multiplying the emissivity times the flux of the box times the area.
Epsilon times which flux of the box? Did they give us the flux of the box?
No, I mean the Q generated.
No. You know why? Look, Q generated is a heat source to the that is given to the rectangular box. بس مش كلها بتروح emission. صح؟ You have a balance here for steady state operation. When you sum your sum of, if you want, of Q dot in will be equal to sum of Q dot out. Okay, so here you are gaining heat due to the generated flux. You are gaining heat due to solar flux, and because you are in steady state, you should deliver back this heat in form of outward flux, which are through convection and through radiative transfer. Okay,
so it's Q total, we can say it's Q total.
No, here the emission flux is due to radiative properties. You know that a surface, what you remember, what is the formula for radiation from a surface?
From a surface, it's the coefficient, I forgot the name, 5.6.
Yeah, very good. The Boltzmann constant.
The Boltzmann
Boltzmann
coefficient
constant.
times the
Yeah,
either emissivity or
exactly,
absorptivity,
exactly.
times
So,
the
so
area
guys,
if
yeah, so
times
here's
T
the
power 4.
challenge in this problem, okay? What is challenging a little bit is that we changed the form of radiation you are familiar with. In general, you have two surfaces, okay? One at temperature T1, the other at temperature T2. You say that because of this difference in temperature, this surface will emit a radiative flux equal to epsilon of the surface times the Boltzmann constant times the area of surface 1, okay, times what? Times the temperature T1, okay, to the power 4. Okay, so this is in general how you express your flux emitted from this surface. And in case it's receiving a flux from another surface, okay, so let's say you have another surface that is emitting a flux that is received by surface 1, then you say that the received flux is epsilon times sigma times A1 times T2 to the power 4. And then when you do the balance, you are familiar with the expression that the total radiative flux will be equal to epsilon times sigma times A1 times T2 to the power 4 minus 2 T1 to the power 4. This is what you are used to do, okay? Here it's a little bit different because instead of giving you another surface and giving you the temperature of the surface and doing like a net flux of radiation, you still have radiation from the surface. So this flux is still present, but the received one is replaced by Q dot solar that is absorbed. Okay, so this is why you should know how this formula was derived to understand that to write it, I should have two surfaces and I should know their temperature. If I just have one surface, it can just emit. It can receive, of course, through other forms, heat fluxes. But if it's alone, it can emit by radiation without receiving. Here it's receiving in solar form, which is also a radiative exchange. But anyway, whenever you have a surface, okay, it can just emit a flux by radiative transfer, okay? And now, after writing Q dot emitted, so if we want to write the expression of Q dot emitted, you have that Q dot emitted here is epsilon times the Boltzmann constant times the area times the temperature of our surface Ts to the power 4. Okay, so in this case, we have expressed all our fluxes. We have found the expression of Q dot generation, which is due to a volumetric heat generation. We have found the solar flux absorbed, and we have found the expressions of fluxes that are emitted by the rectangular box by radiative transfer and by convective transfer. Okay, now once we are done with this step, we are ready to move to the final step. They told us that we are in the case of a steady application. Whenever you are in a steady application, this means that you don't have storage of energy in your system. So the summation of fluxes getting in is equal to the summation of fluxes that you are losing. Okay, so now you say, since it's a steady state application, so okay, we don't have space anymore. Let me open a new file. Okay. Okay, so now I will just say I have a steady application, okay? When I have a steady application in energy, this means that summation of energy fluxes that I gain is equal to a summation of fluxes that I am losing, okay? So I can write then that the variation of energy within my control volume with respect to time is 0. And we know that the variation of energy with respect to time is equal to summation of Q dot N, okay, plus minus, sorry, summation of Q dot out. So I deduce that in this problem, I should have that sum of Q dot N is equal to sum of Q dot out. Okay, now I gained heat through what? Through which processes I gained heat?
Volumetric from the inside,
Yeah,
and from solar.
Exactly, from volumetric and from solar. Okay, now if you remember, just some remark concerning replacement. We said that the value of Q dot generation, so here Q dot N include Q dot generation plus Q dot solar and this is equal to Q dot convected plus Q dot emitted by radiative effect. Okay, now let us replace. Now I don't want you, of course, to solve. You will get an equation and you have one unknown, which is the surface temperature. No need to solve for it. I just want you to reach this equation. And as the question was to write the steady state equation, which will give us the temperature of the top surface. This was the question. Okay, so we have first, as we said, the generated flux is equal to 20 times A. Now, for the solar flux, let us replace, okay? We said for the solar flux, it is equal to alpha. Alpha is given, okay? Alpha is 0.95, okay? So we have 0.95 times the solar flux given was 400 watt per meter square. So we multiply by 400. And we multiply by the area of the top surface, which is equal to A. So times A. Okay. So now, as you can see, A is appearing in both terms. Now, if we move to the other side for Q dot convection, okay, keep in mind the for convection, what is the formula? HA delta T. Okay. Now, delta T is, as we said, T surface minus T infinity. Now, whenever you have a difference in temperature, you can have both temperature in degrees or both temperature in Kelvin. It doesn't matter. Why? Because if the difference between degrees and Kelvin scale is a constant, okay? So even if H is in watt per meter square, you can express both in degrees. But here, what is the challenge here? The challenge is that you don't know the value of TS and you want to write an equation to give you TS. This is why TS should have the same unit in the whole equation, okay? And we'll see that in radiation, TS should be in Kelvin. So please, you should verify that TS is in Kelvin everywhere. So this is very important. If you put T infinity here in degrees, this means that also TS should be in degrees. And since you are dealing with the same variable TS, you cannot put it in certain terms in degrees and in other terms in Kelvin. This will give you a confusing value at the end. Okay, so to be on the safe side, because in radiation you need to use Kelvin unit, you should keep also for all your temperatures, for all temperatures in your equation, you will keep Kelvin because TS is unknown. If it was given for you, it's fine if you replace it here in degree, but also T infinity will be in degree because delta T in degree and Kelvin is the same. I will give you an example. If you have a temperature of 5 degrees and the other 10 degrees, and you want to calculate delta T, you get delta T equal to 5 degrees. Now, if you transform to Kelvin, all you have to do is to add 273 to both temperatures. Since you are adding the same amount for both, whenever you do the difference, the 273 will cancel out, and delta in Kelvin will also be 5 Kelvin. This is why we say that if I know both temperatures, I can or use both in Kelvin or use both in degrees. This will not affect my result. But because here TS is not known and will be included in other expressions as in Q radiation in Kelvin, so here also it should be in Kelvin. Okay, so this is why when I do minus T infinity, I should not put minus 25 degrees. I should convert to the Kelvin unit. Okay, now H is given and the unit it's 5 watt per meter square Kelvin. Okay, so and it doesn't matter if they give me H in watt per meter square Kelvin or watt per meter square degree, it's the same, as I told you, because delta T in Kelvin and delta T in degree is the same value. So I will replace H by 5. The area is unknown. I will keep it A. Now for TS, I want to find an equation to get TS. So this is my unknown. I put TS minus, instead of T infinity, which is 25 degrees, I make sure to switch to Kelvin. So I should add to it plus 273, which is equal to 298 Kelvin. Okay, so minus 298. Okay, plus, now for Q dot radiation, okay, what was the expression of the radiative flux? Epsilon. So as we said, Q dot radiation is epsilon times the Boltzmann constant times the area times the surface temperature to the power 4. And of course, this surface temperature is in Kelvin. Okay, the Boltzmann constant, you don't have to memorize it, of course. I will give it to you. And in case I don't give it, keep it sigma. Okay, so do not replace it, it's fine. So then, but I will replace it here. I gave you that epsilon is 0.9. Now, for the Boltzmann constant value, it's 5.67 times 10 to the power minus 8.